Hello everyone, my name is Jacoby Bussey and I'm a TA for Econ 210, and today we'll be going over problem set 4, question number 1, which has to do with the Malthus model. So this is an interesting model, and so the key idea here is we have a new equation for our growth rate of the population, right? And so our typical things in the solo model is the same. So we have our YT is still the same as A, K. But instead, this time, capital is fixed. We presume that capital is something like land, and land is constant. You can't make any more land, it stays the way it is. Therefore, instead of capital changing over time, capital remains the same. Okay, so that's the equation for output. And then also we have this where we have KT is equal to K where K is greater than 0, which is what I was trying to say. Okay, and so from there we also have this. So our equation for the population in the future is, this is familiar to us, right? So it's 1 plus n, but this time n is a function of YT, and this is in per capita terms. So the growth rate of the population depends on the average income in the economy, which is output. Okay, so how does that work? Well, here's our equation for that growth rate. It is this. YT divided by YL minus 1. Okay. So the idea is, as the income increases, same thing as output, then as this increases, the amount of people in the country should grow. That makes sense. Maybe when you have more resources to spread around, you maybe have more kids. Okay. And so there's also this level right here. This is YL. This is this subsistence level of income. So, and it's also small, but it's also greater than 0. Okay. So let's get started on this model. What does it have to say about, for example, changes in technology? So first we have to derive the fundamental equation of the Solow model in this case, right? So it says that is find expression for KT plus 1, where KT plus 1 is equal to K, which is constant, that's why there's no T's, n plus 1, which is only a function of K2. Okay, so how do we proceed on this? So typically when we do a Solow model, right, we usually utilize our investment equation, right? We use our investment equation, and then we figure out how much capital we need to increase in the next period, right? Well, in this model, capital is held fixed. So if capital is held fixed, that means that we kind of have to look at this a different way. Okay? And so luckily the problem gives us a nice hint in that we're going to have to use KT plus 1 is equal to K divided by NT plus 1. Well, we already have the equation for NT plus 1. It's just this. NT 1 plus NYT divided by YL. My apologies, that was YT minus YL minus 1. Okay. So what do we do now? Let's start simplifying. So 1 plus YT divided by YL. Okay, so we have these ones that cross each other out. And so now we just have KT plus 1 is equal to big K divided by NT. And this is YT divided by YL. All right. So is there anything further we can simplify? Well, yeah, because remember, KT divided by NT is the same thing as per capita, right? So from here, this is just equal to small kt divided by yt divided by L. And so we know from algebra that this is just the same thing as this. We can flip the bottom and the denominator up here. Okay, so are we done? Not quite, right? Because we still have to put this, we have to put everything into per capita capital terms. Okay, well, this is output per capita. Let's see if we can manipulate that. Okay, output per capita is the same thing as output by NT. Okay, and this is just A, K, which is in our case a constant, LT 1 minus A. Okay, and remember we presume that everything else in the Solow model was the same, including the fact that everybody works. That's why this is just this. Okay, so now from here we can just subtract 1 from the exponent. So we have A, K. Now it's just like the Solow model, isn't it? It's just A, K divided by L, A, which is just A, K, T. Okay, so now we know that output per capita is just the same thing as A, K, T to the A. Okay, so from there, let's plug that in to our equation that we've had right up here. So we have YL KT divided by A KTA, right? This is the same thing as K times KT 1 minus A. Okay, so now it's all in per capita capital terms. So let me just write it down. This L A KT 1 minus A. Perfect. That's the first step. We have officially made our equation for our fundamental equation. What's next? Well, the question now asks, draw the phase diagram for the Solow model in this case. Does the model predict that the population converges to a steady state? If so, what is it? If not, explain why not. So let's start with the first bit, right? So first, we need to make a phase diagram. So just like typical, T plus 1, KT, a 45-degree line, and now we have this. And so still we know that it's in this shape because it's 1 minus A, right? If it was 1, then if this was KT raised to the 1, in that case it'd just be a linear line, right? But because it is 1 minus A, we know that A is in between 0 and 1. We know that this is sliding in. Think of like a square root function. Okay, so we know that it will touch at some point KT star, right? We don't know what that point is yet. We'll figure it out soon. This is our equation. Okay, so now what we do next? So from here, right, we need to figure out does the population go to a steady state? Because that's an interesting question, right? So typically when we do this, we think in terms of, okay, does output go to a steady state, right? But now we're asking in terms of population. How do we go about this? Well, again, we can't really go about this the same way we would typically, because output is really just changing based upon the amount of people, right? Where the output per capita is only changing based upon the amount of people. So from here, let's write down some equations that we know about NT. We know that NT is equal to, NT is involved in small kt NT. Okay. We know the equation for KT here, right? It's involved in this. We also know that this is just constant. So technically, we can manipulate this and say NT is equal to big K divided by KT. Okay, that's a start. That's not what it is in the steady state, right? This is the equation for NT. That's not the steady state. How we get the steady state? Well, remember, this doesn't change. This does change. If we want to find the steady state for NT, we're going to need to find the steady state for capital per capita. Let's do that. So typically, when we're finding the steady state for something, we have to think about in terms of what does steady state mean? The steady state just means that we are at a point where we are no longer changing output per capita. Output per capita is remaining the same forever. And that would happen if KT plus 1 was equal to KT minus 1, or rather KT at time 0. Okay, well, that would mean that KT plus 1 minus KT is equal to 0. And we have the equation for KT, right? KT plus 1 right here. Let's use it. So we have y divided by a, yl rather, KT 1 minus a minus KT is equal to 0. Now we just have to solve for KT. So let's add KT on both sides. Okay, now let's divide KT on both sides. So YL divided by A, KT divided. There we go. Now let's multiply A on both sides. Now divide by YL. And now finally, let's raise both sides to the 1 over negative A. Well, this is just the same thing as flipping whatever's inside. This is our K star. This is our steady state for capital per capita. Okay, so we have the steady state here. We can use that for our equation that we had up above, right? So big K divided by small k. So that means the steady state for n is just big K divided by small k star, which is just big K divided by YL over A, right? And so really, you can make this a little easier on yourself, and you could just say it's the same thing as big K SLA A, which is also the same thing as just this. Right? And so this is a lot easier to look at. Let's just use this. Okay, so now we have our equation for the steady state in terms of population, right? And so we do know that the population converges to a steady state because we found an equation for it, right? Okay. For an economy at the steady state, this is for C, suppose that there's an increase in technology A. So technology is going to go up. Show how the phase diagram changes and draw the time path for income per capita, YT, and the population NT after the change into words. Okay, so for the economy at the steady state, let's redraw our phase diagram. Okay, this is our 45-degree line. Let's go back up to our equation right here. That was YL divided by A, KT, YL, A, KT, 1 minus A. Perfect. Nice. All right. And so now from here, we know that this is steady state time T0. But then we're going to say, okay, let's raise our value for technology. Technology is in the denominator in this equation, right? And notice, since technology is in the denominator in this equation, what we're going to do is bring it down. This is where we were initially, and now we're going down here. Right, and so this is the new line that we're on, and so this 45-degree line is above our line, so we're going to the left, and then we go right here. So let me make this double star, and we're going this way. Okay, so let's draw this. And so we're going to draw a time path to showcase what happens to KT. And you really want to do this just about everything. KT. Okay, so at time T0, something happens, right? What happens? Well, technology goes up, right? So if this goes up, this goes down. And so now what we're going to do is we're going to have our new, here we go, T, let's say. And so now this goes down. And so now we know that technology is also going down over time. Because look, not technology rather, capital per capita. Because look, it's sliding down. And we're also going to slide on down like this. This new steady state. Okay. But the question is asking what happens to output, right? So output's a little bit more tricky. And so whenever you're writing an equation, whenever time you're trying to write a time path for another equation, you always want to write, rather for a variable, you always want to write down the equation for that variable. So in this case, we're thinking about output, right? And output, remember, it's just A, K, T to the A, right? So what happens at time T0? Well, remember, technology has increased, right? Technology has increased. It's gone up. So what happens first? We should see a pop, right? So if technology goes up, this also goes up. Does that make sense? What happens next? Well, we see that it goes down, right? The question is, how far down does it go? This is Y star, right? But where's the steady state? Does the steady state above this initial point or is it below this initial point, right? Interesting question. Let's try to figure it out. So from here, what we're going to do is we can just plug in our steady state for KT inside this equation. So A, then we have, let's see, K star was, yep, YL, A, to the 1 over A, right? So these cross out, that gives me 1. These cross, YL. And see if we solved for YL at our initial, remember, and notice, by the way, right? The steady state for output doesn't actually depend on technology. That's a very important point. So output in the long run remains at YL no matter what happens in the long run. Because look, YT is just equal to YL at the steady state, right? Y star. So even though there was a little disturbance at time t0, as it goes on, is always going to go back to y out, right? So y double star is going right back to where it was. Okay. So now we know what happens to output. We know what happens to capital. Let's see what happens to people. Okay. So let's, again, whenever we're writing a time path, we always want to have the equation for the thing that we're working with. Okay. And just to be clear, the reason why this is sliding down in the same fashion as KT is because look at the equation. Once we pass T0, right, A is now constant, is now A prime. But as time progresses, KT continues to go down. So if KT is continuously going down, that would mean that YT also has to continuously go down. That's why it's sliding down like that. And it looks exactly like our KT1. Okay. So the next thing we're trying to figure out is the equation for NT, and we know that is just equal to so N, let's rewrite it. So we have K, well, K is equal to N, K divided by N. Okay. So that means N is equal to that. Okay. And so what happens here? Right. So we know where the steady state is. And so we notice that a steady state we have our A inside our steady state. So we know technology has increased, and we know the steady state should go up. So at the end of the day, we know that this should increase, right? Because everything else here are constants. But how does it change? Let's see. Okay. If technology goes up, right, this brought per capita down, right? And if per capita is going down, well, then what's going to happen to N? Well, that means N is going to go up. Because look, it's in the denominator. So if this goes down, this brings this entire thing up. And does not pop because N in itself at time t0 is not a function of technology at t0. Okay, so this is going to go down. That means this goes up. So that means we're going to fill this in. And this, we're at N star here, but now we're going to go to another steady state right here. And double star. Okay, so KT, this is the exact opposite. So typically, whenever we have our KT going down, all the other equations tend to go down with it. Whenever KT goes up, all the other ones go up with it. In this case, right, it's very important to look at the equations. In this case, KT is on the bottom, right? It's in the denominator. So because in the denominator, if this goes down, that means this one should go up. If this goes up, this one should go down. Okay. And so from that, we know what's going to happen to each of these variables. The last question asks, discuss the differences between the Malthus and Solow models, predict how the economy responds to improvement in technology. So there's some obvious differences here, right? So if you remember from our Solow model, when technology increases, right? Obviously, when technology increases, this should go up, right? It should go out like that. But no, it's actually going down here. That's different. And more importantly for output, right? Technology should increase output over time. So there should be like a new steady state with a higher level of output. But in this model, right, it just bounces back. So why is that, right? I guess the key idea here is that in the Solow model, when we increase technology, we have this higher steady state because the steady state of y is not always going to be constant. The steady state of y here is always going to be YL. It's always going to be YL, no matter what. And so in that case, right, the Malthus model can only show that there's going to be a little jump, but it's going to bring it right back down. And so the idea here is like, what's it called? Whenever you have a higher value for uh, for output, right? Whenever that happens, that means you're gonna have more people to feed, right? Because remember, people have more babies in this model. People have more kids when they do better, when they're doing better financially. So if that happens, then that means these extra people kind of shrink out the effects on output, right? So initially, this is a nice little jump, and it was like, oh, this is great, but then people have a bunch of kids, and now, oh my gosh, all the benefits we got goes away, right? So that's kind of the key idea with the Malthus model. The Malthus model breaks down over time, as we saw, because it doesn't necessarily hold. If you look at the graph here on your sheet, it breaks down very, very quickly after the Industrial Revolution, certainly. Okay. Well, thank you so much for listening. Have a good one.